Hello, Essence. How are you?
I'm good. How are you?
Good, good. Excellent. And everybody else is coming. Sahoda and Kita. Everybody is coming. All righty. Okay. Oh, shoot, I got to get my camera up. Today I'm not orange. Wonder what the difference is. Good morning, Leon. Brian, Celine, how are you? How is everybody? Good. Let's see. Go to share screen here. So, somebody slacked me. Astra slacked me and said, dude. Oh, wait, was it Astra? No, that wasn't Astra. Anyway, somebody slacked me and said that they were like not super following the not super following the combination. You know, it's a weird thing, really, when you think about it. Like that. I guess it's a weird thing, and it's also sort of like an obvious thing that if you take two atoms, right? I mean, you got to accept a bunch of crap, right? First, you got to accept that this is actually the way they look, and it is. It's so wild, but it is actually the way they look, right? But once you accept that, right, then okay, then there are these literally atoms have all these weird looking lobes, these globular things around them, and uh, and so if you place them in proximity of one another, they simply add. Like these two 1s functions, they simply sum. You know, I mean, probably a lot of what is kind of confusing about this is that there's like two spheres. If you think about them, they would look more like, it would more like be a bulge at the belly, if you just added them up. And I think that's a more proper way than this depiction, right? If you just like, I don't know, it's like, so if you just took this in one dimension, it would be this sort of Gaussian looking thing, right? And this Gaussian looking thing. And if you added them in one dimension, it would be like this, it would sort of like bloom, bloom, it would have like these two Gaussian bumps. Now, these don't exactly look like that, but they're pretty close. I don't know, it could be they look exactly like that. Now, the thing about this one here, is that this Gaussian is going up and this Gaussian is going down, right? So when you add them, the ups and the downs cancel in between the nucleus, and the only so the way that they can add together is destructive, and it creates this node in between the nuclei, right? And it just so happens that this is equally repulsive. This is attractive and this is repulsive. And the attractiveness and the repulsiveness pretty much exactly cancel. As far as I know, they exactly cancel, but I know that there's always refinements to the potential energy part of this that you can put in that chain. It can kind of mess that up a little bit. So, who was it that slacked me on this with this question? Is my audio off?
Now you're coming through.
No. Good. Okay. Alrighty. Shutting up, I don't know. So, okay, great. There actually is a YouTube that I want to recommend on this, and it's by Professor Dave, and it's on Particle in a Box, right? So can you guys see Professor Dave?
Yeah.
Yeah, good. So let's watch a little Professor Dave here, and this is about how you can. It's an example of how you solve a differential equation to get a solution to a quantum question, right? So let us see here. Can you hear it?
It's not playing.
Yeah.
Right.
Can you guys hear it? Okay, but it had this little song. Could you guys hear the song?
The video
okay.
isn't played.
I have to turn the. I know, but okay, I'll turn it on and I'll see if it.
Yeah, we can't hear this.
No.
Can you hear the? Okay, good, excellent, good. Whoops.
No, we can't hear this.
Can or cannot?
Can't.
I don't think you're sharing your computer.
Can't. Okay, so how do I do this again? You go to like maybe audio or?
I think you have to reshare your screen and then specify that you want to share computer sound.
Okay, so I go to new share. I go here. Oh, and share sound. There we go. All right, thank you.
our first quantum problem. This will be to
Yeah?
find the eigenenergies and eigenfunctions of a particle in an infinite square well. This is also famously known as the problem of the particle in a box. We assume a potential which is as follows. V of x equals infinity everywhere except between x equals 0 and x equals a, within which it equals 0. Let's unpack what that means a bit. We are probably familiar with the concept of
Dr. Terrill, can you please go
an
full
electrical
screen?
potential.
Can I go? Oh yeah. I will. Sure. I'll try. I'll try. It could.
Or gravitational potential. And we know that an object will have a tendency to go towards a lower potential. A ball will fall from some height where
All right,
it has
thank you.
greater gravitational potential
Excellent.
energy down towards the ground, its potential decreasing as it goes. A compressed spring will relax from a state of higher elastic potential to attain its equilibrium position. So here, when we say that v of x equals infinity for these intervals, this is the mathematical way of saying that the particle is definitely not there. That may seem counterintuitive, as it sounds like infinite potential should mean that it certainly is there. But remember that objects proceed towards a lower potential, and infinity is the opposite of that. So we know the particle is sitting in this square well. The only thing is that since we are looking specifically at a quantum particle, we have to use the Schrödinger equation to figure out where, or more accurately how, the particle lives within these walls. So now what we want to do is to find the wave functions psi of x representing this particle which satisfy the Schrödinger equation. This is the same as asking what are the allowed states for a particle that lives between these walls? What does its probability density function look like under these conditions? And also, what are its allowed energies? All of these answers will arrive from determining which wave functions satisfy the boundary conditions imposed by the potential and the parameters imposed by the Schrödinger equation. The boundary conditions tell us something right away. As we said, the particle will surely not be located wherever the potential is infinity. That means that for those regions, the probability density function must equal 0. If the particle is not there, the probability of finding it there is 0, and the probability density function is equal to 0. The probability density function is psi star times psi, so the only way for this to equal 0 is for psi of x to equal 0. Therefore, we are looking for a wave function that will satisfy the following requirements, where psi of x equals 0 when x is less than or equal to 0, and also when x is greater than or equal to a. But between x equals 0 and x equals a, the wave function does not equal 0, and its value can be determined using the Schrödinger equation. Let's use our new time-independent form of the equation, which as we know looks like this. We will find that isolating the partial derivative will make things easier, so let's move all of these constants to the other side, which will entail multiplying both sides by negative 2m over h bar squared. So now the second derivative of psi with respect to x is equal to negative 2me over h bar squared times psi. Let's do another trick to simplify further. Let's define k as the square root of 2me over h bar, so that k squared will be equal to 2me over h bar squared. We can plug that into our equation to simplify the right side, which will now be negative k squared psi. And finally, let's bring this term to the left side by adding it to both sides. So we have the second derivative of psi with respect to x plus k squared psi equals 0. This is a second order differential equation, which we need to solve in order to find psi. And as we know, psi depends on x. Solving this differential equation entails finding all the forms that psi can take to satisfy this equation, just like solving a quadratic algebraic equation entails finding the values that x can take to satisfy the equation. There are simply different rules that must be used to find the solution. For example, if psi of x is equal to x, then when we take the second derivative of x with respect to x, the first derivative is 1, and the second derivative is 0. That leaves us with k squared x equals 0, which can only be true if either k or x equals 0. K can't be 0 because K depends on energy, and if energy is 0, we don't even have a particle to begin with. And in this case, x can't be 0 because psi equals x. Therefore, if x is 0, psi is 0, and the probability density function equals 0, which once again means that the particle does not exist. So this is not a useful solution because we know that there is a particle. This is a condition for the problem, so we would need to try something else. Now for brevity, rather than continuing to go through many possibilities, let's just state outright that the solution to this differential equation is of the form psi of x equals a sine kx plus b cosine kx, where a and b are constants that we don't know yet, but will determine by using the boundary conditions, and k is as we defined earlier. This may seem out of left field, but this general solution is arrived at through some clear-cut rules that are best omitted here to be covered over in the mathematics series for those who are interested. But this expression represents the solution of the time-independent Schrödinger equation between the walls of the well. Just to quickly prove that this is the solution, we can plug this expression into our rearranged version of the Schrödinger equation. This first term involves taking the second derivative. So let's take the first derivative first. Remembering that the derivative of sine is cosine, and the derivative of cosine is negative sine, and also that the chain rule requires that we bring k out front for each term, that will give us ka cosine kx minus kb sine kx. Then we take the derivative again, and we get negative k squared a sine kx minus k squared b cosine kx. Then we add to that k squared times the original expression, and distributing k squared, we get k squared a sine kx plus k squared b cosine kx. So, as we can see, everything cancels out to give us 0, as should be the case for any solution according to this version of the equation, which means this does indeed satisfy the Schrödinger equation. So combining this with what we said before, psi equals 0 when x is less than or equal to 0. Psi equals this expression when x is between 0 and a, and psi again equals 0 when x is greater than or equal to a. Let's now try to understand this graphically, as it will provide us with some understanding of the solution. As we said, the wave function must equal 0 at the boundaries. This means that psi of 0 equals 0, and psi of a equals 0. Now, since we have two different trigonometric functions to consider, it will be easier to examine them separately to get a sense of how they combine to give us the value for the wave function. Let's first remind ourselves of what sine of x and cosine of x look like. One important thing to notice is that sine of 0 equals 0, and cosine of 0 equals 1. This means that no matter what value for k we have in our expression, sine of k times 0 is still sine of 0, which will always be 0, and cosine of k times 0 is still cosine of 0, which will always be 1. This means that in order for their sum in our expression to equal 0 when x equals 0, the constant b must equal 0. That means we can simplify our expression and get rid of the cosine term entirely. That leaves us with psi of x equals a sine kx. Now let's examine the other boundary. Psi of a must also equal 0. This could be achieved by setting the constant a equal to 0, but that would mean that psi of x equals 0 for all values of x, which again means that the probability density function would equal 0 for all values of x, and there is no particle, so that is not a useful solution. The other possibility is that sine of kx equals 0, and we are specifically examining the boundary where x equals a, so sine of ka must equal 0. Looking back at our graph of sine of x, we know that it is equal to 0 at x equals 0, and again at pi, and 2 pi, and every successive multiple of pi. Therefore, sine of ka equals 0 when ka equals n pi, where n is any integer. This also means that k equals n pi over a. Let's again examine this graphically. To make things simple, let's set a equal to 1, and then examine the graphs of sine of kx, which will therefore be sine of n pi x, and see what happens with different integer values for n. Each of these n values gives us a solution to the Schrödinger equation. We can see that in each case, the wave function has a value of 0 at both boundaries. Recalling that k depends on energy, if k also depends on n, then energy depends on n, and each value of n is giving us a different wave function, or eigenfunction, and a different eigenenergy for the particle. These are the allowed states for the particle. We can see how quantization comes into play here, as n must be an integer in order for the sine function, and therefore the wave function, to satisfy the boundary conditions. The fact that n must be an integer is what imposes quantization on this system. We have just one more thing to do. We have not solved for the constant a, so we still don't know precisely what the wave function looks like. In order to do this, the wave function must be normalized from 0 to a. As we recall from a previous tutorial, we will use this bracket notation to represent the normalization of psi, which will equal the integral from 0 to a of psi star times psi dx. And because we are normalizing, this must equal 1. Now, in this case, psi is a real function. There are no imaginary terms. So psi star times psi is the same thing as psi squared. So let's just square our expression for psi and put that in the integral. That gives us a squared, which is a constant that we can pull out of the integral. And inside the integral, we have sine squared kx dx, which again must equal 1. Now we have to solve this integral, and if we are a little rusty with our integration, we will have to remember that we can use a trigonometric identity here. Sine squared theta can be expressed as 1 minus cosine 2 theta over 2. So let's apply that identity here and change our expression into 1 minus cosine 2 kx over 2. Let's make this simpler by splitting it into two terms and giving each its own integral. So the integral of 1/2 dx minus the integral of 1/2 cosine 2kx dx. And we can evaluate these separately. The integral of 1/2 is simply x over 2. And plugging in our values, we get a over 2 minus 0, or a over 2. And the other integral isn't much harder, since we know that the antiderivative of cosine is sine. So we get sine 2kx over 2. But then we have to put an additional 2k in the denominator, because we are basically doing the chain rule in reverse. And that will cancel out the additional 2k in the numerator that would occur if this were being differentiated. So now we plug in our values. First we plug in a for x, and then subtract from that the same expression but with 0 for x. Anything times 0 is 0, and the sign of 0 is 0, so this whole second term is simply 0. Now let's put the results of these two integrals in parentheses so that we can bring back a squared, and then we can make another substitution. We know that ka equals n pi, so let's make that change. We know that n must be an integer, and we know that the sign of any multiple of pi must be 0. So this entire term will actually be equal to 0. That leaves us with simply uppercase A squared times lowercase a over 2 equals 1. Just a bit more algebra and we find that uppercase A must equal the square root of 2 over lowercase a. And now that we have solved for a, we can express our solution as a set of wave functions, which are the eigenfunctions that satisfy the Schrödinger equation for the boundary conditions given by the square well. So psi sub n equals root 2 over a sine k sub n times x, where k sub n equals n pi over a, where each integer value of n gives us a different wave function. So when n equals 1, we get psi 1. When n equals 2, we get psi 2, and so forth. Each of these wave functions has an associated eigenenergy. Using our definition of k, we can now express E sub n as being equal to h bar squared k sub n squared over 2m. And given that k sub n equals n pi over a, this will equal h bar squared n squared pi squared over 2m a squared. Again, each integer value of n will give us an eigenenergy which describes the corresponding wave function. And there we have it. So that was definitely a bit of work, but we have successfully solved our first quantum problem. We determined the allowed energies of a particle in an infinite square well, given certain boundary conditions. Even though the problem has been solved, there is still a lot to discuss in terms of the implications of the solution, which will require an entire tutorial unto itself. So let's move forward and get some more perspective on the particle in a box.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. Had to go pee. Oops. Go away.
Unprotected machines like this one are ripe for random phishing attacks.
All right. Shut up. Let's see here. So, so I wanted to show that basically so you could see an example of like how somebody could get through an equation problem like this, right? And it's a classic problem. We've been using it to torment undergraduates for years. I was tormented with it when I was an undergraduate, you know. And it's like one of the few fairly straightforward solutions. And the main thing about it is that you just throw this differential equation, h bar squared over 2m d squared x d psi squared equals e of x. Like that's the differential part of the equation. Then you try different solutions. Psi equals x, psi equals all these different solutions. And you get to one, you know, psi equals a sine kx, b cosine kx, right? They should have just used sine because the cosine drops out anyway, but and then that fits, right? Then it's true that, you know, the second derivative equals e times psi, right? And then you just plug in that equation and you start chipping away, you get the constants, you normalize it, and everything's good, right? And that's how the hydrogen problem was solved, right? And the H2 plus was solved that same way, right? And they got these sinusoidal functions, most of which have what's called a real and an imaginary part, meaning they have a sine and a cosine term. And well, yeah, because the imaginary part comes from Euler's theorem, which is e to the I theta equals sine theta plus I cos theta. So you can solve differential equations using that formalism. But once you do, then you get these functions and you recognize right away that there's nobody with anywhere near the horsepower to solve this for anything but the simplest conditions, right? And so so what we do is we say, well, instead of solving for the exact psi, let's take approximate psi values and calculate E, right? Since the second derivative equals E psi, right? We can just try a psi value, and then you can take Schrodinger's equation and solve for E, put in a function and get an E value out, right? And when you do that, there's a well-founded postulate that says that the wave function that results in the lowest energy is the best wave function, or is better than one that results in a higher higher energy, right? So so basically you can solve for different E values that way. And I think that's all that probably I should say about this. You know, and what I want to talk about today actually is an extension of this theory to crystals, right? And you can say, like, if you ask yourself, you know, what is a nanoparticle? How do they work, et cetera? Well, you have to understand crystals, right? You have to understand the electronic structure of a crystal. And this was first solved by Felix Bloch, who was, as it turns out, Werner Heisenberg's first PhD student. And a little aside here, Heisenberg was a close friend of Niels Bohr, and he was a real Renaissance man in Germany, right? But he grew up right around the time Hitler was rising into power, right? And he spent almost all that time with a group of other youth camping, you know? They went camping for like these extended camping trips. And Heisenberg tried to stay out of politics, but he was deeply patriotic. And so he got on the wrong side of the political spectrum from Bohr and all the other people who wound up working on the Manhattan Project, you know. So it was kind of sad, you know. Heisenberg was a great light in science, but he had to work on the bomb for the Germans and stuff. So that was kind of a break. And but nonetheless, he had a right before the war, he had a PhD student named Felix Bloch, and Bloch left Germany right as Hitler took power. He said, "No, I'm out of here," right? But Bloch had gotten his PhD, and he basically solved the Schrodinger equations for an electron moving in a periodic lattice, right? So we just solved it for this square well lattice, right, which is infinite, zero, infinite. There's the potential energy. Well, Bloch solved it for this periodic energy potential, right? So it's going up and down and up and down, right? And there's a pretty good Wikipedia page on this also, but the basic idea is that if you can solve this equation for, say, a hydrogen atom or whatever, right? And then you can extend that to molecules by summing the equations, and you get, it's like there's an atom. Let me go to my little stupid docucam here real quick, and then I'll try to. The idea is that if you can solve the equation for a particle, a molecule, then you can use the same principles to think about solids. So let me change my share here. So for for a hydrogen atom, you've got these. You've got these many n values, And then for a molecule, right, you've got the atomic wave functions summing into molecular wave functions, right? And you've got like a sigma, sigma star, sigma, sigma star, pi, pi star, that type of thing. And so you have also, it equates to a similar looking situation, right? But now there's the bonding between the molecule number 1 and molecule number 2 to consider. Now, in a solid, what happens is that you have essentially, you can think of it as an extension of this AA molecule, or this 1,2 molecule here, right? Where you have A and A, but really what you have is like an infinite number of these guys. And so you have an infinite number of states. And then you also have an infinite number of anti-bonding states, right? And so if you have 10 to the 6 atoms, you've got 10 to the 6th states. And a state is really a state is a psi of x, y, z, right? But in this case, there's just an infinite number of them, and they are so closely spaced that you can think of them as there's a certain amount of freedom for the electrons to go between levels, right? And herein lies a sort of a mysterious part, at least for me, right? Which is that let's take a typical example of a semiconductor here, where you have silicon, right? And silicon makes 4 bonds, and if you make a crystal of silicon, you see that only the valence bands are filled, right? You can't see electrons. The anti-bond, or this is the anti-bonding orbitals. They will be completely empty, and the bonding orbitals here will be completely full, right? And that's actually typically the case for the outermost valence electrons in a molecule. But so in silicon, you'll have, this will just be completely full, and this will be completely empty for a silicon crystal at low temperature, let's say. And that silicon will not conduct electricity, right? And the reason that it doesn't conduct is because there's no way to move an electron between atomic centers, because an electron that sees all its neighbors at the same potential energy sees filled states, right? And I don't completely understand why you can't take one out of one end and put one in the other end and just shift everything over simultaneously. But for whatever reason, that does not happen, right? So, so filled states don't conduct, right? Right. So what I would like to do is I'll make some breakout rooms right now, and I want to put y'all for maybe a 10 or a 15-minute breakout into, I'll make 9 rooms, and we'll have a little breakout here. Okie dokie. And we'll, I'll open all the rooms. And what I would like for you to do is to think about this problem and come up with some questions for me about the issue of bands and whether they conduct or whether they don't conduct. Can you do that maybe? Alrighty. Well, try anyway.
Wait,
or you can complain about me if you want to. Yes,
I'm
Vito.
sorry, the issue of what and why they don't conduct?
The issue of like bands. So what we're describing here is band theory. You know, like not like the kind of not marching band, but electronic bands. So solid state electronics, and why in a pure silicon crystal where you have a completely filled bonding band and a completely empty anti-bonding band, that this material does not conduct electricity.
Okay.
All right. So think about that for a couple minutes, and I'll visit the rooms. I'm just gonna fill up my coffee cup, and then I'll be right back. Okay.
Mm-hmm.
Yay. So Hoda, you're frozen. Ah, now you're gone.
Guess questions for Roger.
I need questions.
Yeah.
I'm like a question vampire.
So the if it conducts electricity and not is basically whether it can jump up energy levels.
No. The question of conduction means whether an electron can move through the solid.
So
If
when
there's
the
a gap.
bands are full, it prevents that.
Right.
Why
So-
does it prevent electrons
Right.
from the
Right.
solid?
Yeah. So that you're diving exactly straight into the center of this problem. I love it. And I have a feeling that you are now exactly where I am with this question, right? Why do filled bands not permit the transfer of electrons? Xiaoming, why do you have a mask on?
I'm in the lab.
You're in the lab?
Yeah.
You poor bastards have to wear masks in the lab?
Yeah, because there are someone else in lab. Yeah, because they
All
all
right.
wear mask. Yeah.
Oh my gosh. Oh well, I'm sorry. It's fine. I just have to give them a hard time.
Ah,
So Ankita, tell me about this problem. Tell me what you understand. What am I asking?
I mean, I don't really know.
Okay, so what does it mean for something to conduct electricity?
I guess that it can have like current go through or something.
Mm-hmm. And what is current?
Electricity, so electrons.
Yeah, exactly.
Okay.
Exactly. It's electrons can flow through the material. Okay, good. Okay, so now think about now what we're trying to do is superpose our thoughts about the structure of a solid, the electronic structure, not the positions of the atoms, but the states that the electrons can occupy. Right, and in a material, there are basically two types of states: bonding and anti-bonding states, and those are called valence and conduction bands also, right? And why does a semiconductor with completely filled valence and completely empty conduction band not conduct electricity? But if there's a vacancy in the valence band or an electron in the conduction band, it will. Okay, so I've got to go. I'm going to visit another room.
Roger, can you set me as a co-host? Then I can also jump around.
Okay, sure, absolutely.
I can also go to another room to help them. Or like I need to stay here.
Yeah, absolutely. No, you're stuck there, man. You're stuck. But now it's going to be just Lucas and Ankita. They're going to be stuck. So that's all right. I don't care. Okay, so let's see here.
So in
Participants.
the participants, yeah. The more like I guess.
I'm trying to find when I went into breakout rooms, the floaty thing disappeared for me, and so I don't know where to get to the menu anymore.
Click the.
Here it is. Yeah, here it is. I see it now. I see it.
Excellent.
Participantes. But there's only 4 people in this room. But let's see here.
You can.
Let me see if I
If you move the mouse to cursor to me, like there's a more.
Yeah.
Can you see? I don't know whether you can
More?
set me a
There's 3 dots. No, I'm screwed. You just have to talk to these guys. See if you can figure
Okay,
it
yeah,
out.
Yeah, I can help them.
I'm out of here. I'm joining a different room. Bye.
Okay, bye.
Rohan.
Hello.
I mean Darth.
Oh,
How are you, Darth?
very confused.
Very
Very confused.
Oh, okay. All right. So let's so Brian and Emma. So so I'm talking about the question of electronic conduction, right? So what does it mean for a material to conduct electricity?
Well, I know that question. It has to deal with having free electrons in the sea of electrons with a metal, right?
Okay.
So if it has free electrons, it can conduct electricity.
What do you think,
Right.
Emma?
Well, I would have said something similar with the free electrons in the.
Uh-huh. Mm-hmm. Brian?
From what I got in school, like they just told me that substance is it's conductive if it has free electrons.
Okay. All right. I like that. Okay. So so in a material, electrons cannot have arbitrary energies, or in other words, there are limits to the energies that electrons can have. And there are limits to the states that they can occupy. Like, you know how when we, that whole particle in a box thing, when you work through it, the Schrodinger equation says, and the Schrodinger goddamn equation is right, that there is a state where the electron, the wave function is just like a single peak, and then there's a pair of peaks, and then there's 3 peaks, right? So there's a sequence of states of increasing energy, right? And in a material, it's the same deal, but the states are, we don't know what the states exactly look like, right?
Yeah.
But we do know what energies they have, right? So in the example of silicon, you have, if you have 10 to the 21st atoms of silicon, you got a little chunk of silicon, maybe a cubic centimeter. Then you have 10 to the 21st bonding state. No, wait. 4 times 10 to the 21st bonding states. And 4 times 10 to the 21st anti-bonding states. Right? So that means that there's 4 times 10 to the 21st states which are lower in energy than the corresponding orbitals on silicon when the atoms are separated. But when the atoms come together and they condense, then the electrons, they get choices. They can go uphill or downhill, right? And the downhill choice is always into a bonding state, and the uphill choice is into an anti-bonding state, right? So when you take these atoms and you bring them together, the bonding state starts to fill up, and it exactly fills, except for the ones on the surface. But you got so many atoms that the surface, you can neglect the surface for the purpose of characterizing the bulk. Okay? So the question on the table is, why does that material not conduct electricity?
Because
And
all their electrons are locked together, right? So their
Okay.
electrons can't flow from one state to another or from one bond to another, and they're stuck with the pairs that they have.
That's actually brilliant. But, and that is exactly the way that this type of problem is solved, right? Is you think about electrons being stuck or not, right? Like, are the electrons in the bonding state, are they stuck, right?
Yeah.
Okay. And apparently they are, but there's a reason to believe that they're not actually, like, there's nothing about the state that makes them stuck, right? Because if you were to remove an electron from that state, like take your little cube of silicon and just somehow take a pair of tweezers and pull out an electron, right? The little chunk will be charged, right? But that charged chunk will then conduct electricity. Not a whole lot, but it will conduct. All right. I'm visiting another room. What room are you guys in? I can't even
I
tell.
think we're one.
Anyways,
Oh, yeah,
you're
we're
one.
room
Okay. All right. I'm going to go to room 2. Wait, unless you have questions right away, but I'm good enough. Okay, I'm going to room 2. Bye. Hello, everyone. So, did I leave you like without a proper explanation of the question? That seems to be what's happening. Unmute, for goodness sakes, unmute. How can I unmute you guys? Are you just like staring at each other like with your mute buttons on? Oh my gosh, can you unmute? Yes, yes. Oh my gosh. Ugh. Ugh. You guys had just like a staring contest, huh? You're just like, who's gonna blink? All right. So if you guys are just fed up with everything, that's totally fine. I get it. But my question was like, why does intrinsic silicon not conduct electricity?
I was thinking that like if the bands were filled up, that means there'd be like a restricted flow of electrons. And so because of that, it wouldn't be able to pass through. And that's why you wouldn't be able to conduct electricity then.
That is a perfect phenomenological explanation, right? Because the valence band, the bonding orbital, are completely filled, right? And the valence band, that is the anti-bonding orbitals, are completely empty, right? So that's actually true. So why? But there's all these electrons on there, and why can't you move an electron through that band?
Is it because of the potential energy? So like one state has like a higher potential energy and the other has a lower. So like the movement would take too much energy for that to occur. And so they prefer to stay in like the given band.
That's what I was thinking.
That sounds that sounds really good, actually. Well, what do you think, Jerry?
Yeah, like
These
yeah, something about like the potential energy difference and how
between the
and, like the gap is too much for the electrons to jump and for the silicon to conduct electricity.
Yeah. Okay. So Jerry just said the word jump, right? Jump from where to where?
Like the lower to upper band.
Yeah, right. From the So just to clarify one thing, that doesn't mean that there's any physical movement of the electron, but there is an increase in the potential energy of the electron, right? Isn't that strange, right? Because it could be in the exact same place, but it simply has more energy. Now, how much more energy would it need to go from the valence band to the conduction band, the bonding to the anti-bonding state? Well, it depends on the crystal, right? Right. Good. And so it's a couple of volts. You know, for electrons, it's really easy to talk about voltage. You know, and a volt is a potential energy for an electron, for a charged species, right? So in silicon, it's a couple of volts, right? And that is way more energy than there is available thermally, right? So if there's electrons in there, and if the crystal's at 0 Kelvin, then the electrons are all in their lowest energy states, you know. But then as you start to add energy, the nuclei and the electrons begin to have these modes of motion, right? And that can occasionally, like there can be some sort of like combination of the electrons. Maybe two electrons can come close to one another and be excited from the valence into the conduction band. But let me ask a little bit simpler question. Why does the filled band not conduct? Actually, you guys are doing great. You guys are doing great. And I have to leave, but I want to leave you with that question. You're on track. Everything's fine. You've already aced this one, right? But I got to go. So I'm gonna. I have to go to a different breakout rooms. There we go. You guys are room 2, right? Yes. Okay. Cool. All right. I got to join room 3 now. Bye. Oops.
Hello.
Hey guys.
Hello, Dr. Terrill.
How are you doing?
Pretty good. Just chilling.
Good. So I'd like to clarify the question a little bit. And the question is, why would an intrinsic silicon crystal not conduct electricity?
Okay, I think we have an answer for that.
Alrighty.
So
Shoot.
Oh,
Alicia.
Yeah, Alicia.
wait, sorry. I'm searching up intrinsic really quick.
I'm sorry. A pure silicon with nothing else, just only silicon atoms.
Okay.
Yeah. Just like. Yeah. Okay.
Okay.
All right.
Vigo, do you want to answer, or
Do you have a preference?
I don't have a preference?
You know what, Alicia, you're smarter than me. You can answer.
Oh, no, I don't want to answer.
She does have a preference. She does have a preference.
It's fine. I'll answer. It's fine.
All right.
Essentially,
Okay.
the reasoning is that with pure like solid silicon, it's
Mm-hmm.
not a metallic structure which has free flowing electrons, but rather it's
Mm-hmm.
a crystalline structure which solid crystalline doesn't conduct electricity very well. That's why something like solid NaCl, so sodium chloride won't
Mm-hmm.
conduct, electricity very well. But then you get it like aqueous, and it's like, gosh golly, it conducts very well. So
Okay.
that's essentially, it doesn't have like free flowing electrons or anything like that, meaning that it can't conduct electricity very well.
Mm-hmm. Mm-hmm. Oh God, you brought up electrolytes. So, Ion, what's wrong with this explanation?
Well, with the explanation, because like, I guess it's not like a perfect fit, I guess, between NaCl and silicon, because NaCl is like, it's like a ionic structure where it becomes two ions when you put it in water. Versus
Right.
silicon is
Okay.
usually like,
All right. So the whole thing about putting sodium chloride into water and it's conducting, that is a red herring, because I'm actually talking about electronic conduction, the movement of electrons within a crystal, right? We're not talking about a solution, which is not a crystal, you know, and that type of ionic conduction where ions move through the crystal.
Hmm.
So if we rewind then, the you said that a crystal is different from a metal.
Yeah.
And that is not true.
Okay. Gosh
Yeah,
darn.
because metals on the whole are crystals, are crystalline. They're just different. And so like if you look at the periodic table, the whole left side, they're all crystalline metals, you know, except for hydrogen, right? The whole right side, there's semiconductors and there's nonmetals, right? And they all can be crystals.
is it?
All right.
Oh, is it
Yes,
because
yes.
like silicon has those 4 electrons and then 4 empty valence, like 4 empty valence like gaps? Then it doesn't have a preference for having either more or less, so it wouldn't like transfer electrons.
So if it could transfer electrons between the bonding and the anti-bonding orbitals, between the valence and conduction bands, then that would conduct, but it can't. And so by framing the question the way I am, I'm saying conduction is normal and insulation is like weird, right? And you flip that on me, which is cool, because that's the way you got to approach this thing, right? And so so think about that a little bit, and then I'm going to join a different room and I'll be back. Maybe never, but I will be back, I promise. Okay. Oh, everybody's gone. Okay, everybody but room 8, because I'm going to visit room 8, then we're going to go back to the main thing, okay?
Okay.
Hey, guys.
Hi.
Hi.
Thanks for waiting for me. We went over 2:30 by 7 minutes. A lot of people have gone back to the main room. But how did this, the question was a little bit hard to pin down, but how did you do with it?
It was okay to like.
It's okay. I got some parts of it.
Yeah, we to like fill in our like understanding. We looked it up, right, and like sort of read about it on some websites.
Excellent.
And
excellent.
so our understanding is sort of like there's the valence and the conduction band, right?
Yeah.
And the theory helps explain like insulators, semiconductors, and conductors by describing like the difference in energies between these two bands. And like for conductors, there's a large difference, so it's difficult for electrons in the valence band to go to the
You mean
conduction band.
insulators?
Yeah.
Wait,
Insulators.
yeah. Sorry. Insulators, yeah. And for like the conductors, it's like basically overlapping. So then it's like they're almost shared in a way. So like that was sort of our understanding. Is that sort of correct?
That is definitely sort of correct.
Okay. Yeah. And yeah. With our
Vivian.
About it?
Wait. I want to hear from Vivian. Vivian, how's it going? Do we all? How's just like say hi or something?
Only a little confused, but I just like trying to find online resources to kind of.
Okay, all righty. So the the actual core of what I'm trying to ask is why pure crystalline silicon does not conduct electricity, right? Why it insulates. And I'll go back to the main room now because people are going to be getting antsy and waiting for me, but I'll try to answer that, okay? So you guys did good. Yeah, I don't know. I don't really know either, but we'll take a stab. All
right.
Bye. Okay. I've got to close these breakout rooms already. Okie dokie. So, a lot of you did really well. Everybody did well, I think. But the actual question that I was trying to answer was, or that I'm trying to work towards answering, is why intrinsic silicon does not conduct. And so if you're an electron in intrinsic silicon, like intrinsic means pure, without any atoms other than silicon in your crystal. If you're an electron in there, you will, as you dissipate energy, you will enter the lower states, right? And it's because of the nature of the 4 bonds per silicon, everything is perfectly arranged such that all of the electrons in silicon can occupy a bonding state or a valence state, right? So at low temperature, eventually all these electrons will filter down into this low energy state. And that state does not conduct electricity. And that is kind of cool, right? Because that insulating state, in order for it to conduct, an electron has to move within the crystal. An electron or a bunch of electrons or 2 electrons or something like that, right? And the best explanation that I've heard about this is that that is prohibited by the Pauli exclusion principle. It's almost like if you're in a room and everybody is shoulder to shoulder, right? And it's then you can't get to the door, you know? Nobody can move, right? Because you can't have 2 people in the same place at the same time. And that's basically what the Pauli exclusion principle is saying, is that you can't have 2 electrons in the same quantum state with all the same quantum numbers, you know? So, so I think that's the answer to why intrinsic silicon doesn't conduct. And I apologize if I botched or did not actually ask that question, but that's I think a better question than one I probably started with. So with that caveat, right? So now let's ask another question, which is why, if you substitute a single boron atom for a silicon atom, why then is there why then does that conduct? And let me give you let me turn to our trusty camera thingy. I'm going to try. I have my Documate 2.0. So I'm going to try to explain what happens when you have silicon, 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 boron, silicon, 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 right? So this is what I'm depicting here is a doped crystal. And in a doped crystal, everything about the crystal is dictated by silicon. The structure of the crystal, the electronics of the crystal, everything is sort of dictated by the fact that it is 99.999% silicon. But this 0.01% boron radically changes the qualities of the silicon. First of all, the silicon before that addition of that boron atom was an insulator, right? Although at high temperatures it might conduct a little bit. Because at high temperatures, electrons spontaneously can occupy the conduction band and leave a hole in the valence band, right? So in this structure, right, there's a conduction band, a valence band, and a gap. And this is full and this is empty in the case of silicon, of intrinsic silicon, right? Because every silicon makes 4 bonds, it has 4 neighbors, everything's copacetic, everything's full, right? So now, if you substitute a boron atom into this crystal, boron only has 3 valence electrons, right? The silicon all have 4, right? And so they make these bonds like this. I mean, it's not square, it's tetrahedral, but whatever. And then it bonds there, there, there. And then here is a half-filled bond, right? So this, oddly enough, this actually almost immediately fills with an electron from somewhere else in the lattice, right? But when it does, it leaves a hole behind. Does that make sense? So if there's electrons everywhere and you take one and you say, no, you belong to the boron, because you're going to stay on the boron, then that will leave a hole. That will leave a vacancy. Right? So, and that vacancy can then hop around. It can go from place to place. And if you apply an electric field, that thing is going to go towards the negative electrode. The holes will migrate towards the negative electrode, yeah? So we are close, you guys. We are so close. So close to having a major cognitive breakthrough in terms of semiconductor physics. So just hang in there. Wait, actually, let's all do jumping jacks. Yes, yes, yes. Vigo, come on, Ion, you can do it. Yes. Okay, just arm jacks, just arm jumping jacks. Yes. Come on, Rohan, you can do it too. Come on, buddy. All the guys. Come on, Weehan. You can do it. You can do it. Yes. Yes. Weehan's doing real jumping jacks. Yes. Come on, Jimin. You can do it. You can do it too. Yes. Come on, Ankita. Yes. Sahota. Chris, we're waiting for you. You're the only one not doing them. Yay! Woo! Okay. All right. We did it. Ah, a little bit of blood flow has happened. Ah, okay, good. So now we're sort of awake, right? So now we're going to understand what happens when you substitute a boron into a crystal. The boron makes a fixed negative site and it leaves a hole, right? Can you guys see this? I see what I'm writing down here, yeah, right? Cool. So that hole then, the hole can migrate. And this is called a p-type. Oops, this is not visible, is it? Now it's visible, right?
Yeah.
Okay, thank you, thank you. A p-type semiconductor. P-type meaning, P meaning positive, because and a positive is a hole, and sometimes holes are called H plus, right? Now, what if you put, instead of boron, if you move to the right, there's carbon, right? Carbon has 4. Then we move one more to the right and we get to, let's move to the right and one down. And let's get to phosphorus, right? Now we've got, B minus, H plus, or phosphorus, which starts out with 5 valence electrons. What happens to that guy when it is forced to occupy a tetravalent lattice? Somebody tell me.
There's going to be a negative.
Boron took, okay, yeah, there's going to be a negative electron, right, out there, right? And the phosphorus site will then be what charge?
Neutral. I mean,
positive.
Yeah, so we've gone through the 3 possibilities: negative, neutral, and positive. Who votes for negative? Who votes for neutral? Who votes for positive? We got like 3 or 4 votes total. This is America, isn't it? It's like the voting electorate. Oh, Ion is voting twice. I like that. Excellent. So we've got P, and what happens is phosphorus loses this electron and it becomes plus, right? And so this is a P type, and this is a blank type. Blank is, P is for positive.
And
N type. Exactly, N type. Very good, Ion. Excellent. Right? So we've got P type and we've got N type silicon, right? So N type silicon, they conduct, but they conduct in different ways, right? So if you have now the 2 bands here, you can have bands where there's there are positively charged holes and then you can have an electron, and this will make N-type, and this will be in the conduction band, and this will be in the valence band, right? So just by adding just a tiny amount of dopant, you can dramatically affect the conductivity of silicon. It can go from, conductivity of 10 to the minus 6th to 10 to the 0. You can change by 6 orders of magnitude, right? And you can do that by substituting with boron, and you can have both, but it's not as common, right? That would be called a degenerate semiconductor, right? Where you have both holes and electrons, and they behave a little bit like metals, I think. I don't know, but so if you have this type of semiconductor setting, right, and you have one where you have p-type, and you make a contact between that and an n-type semiconductor, right? And you have like a junction here. I don't know. I shouldn't make a, I'm just gonna redo that. I'm just gonna have, if you have, this just silicon, and maybe there's a sort of a region here where this is n-type and this is p-type, right? Then what happens is that this electron diffuses across the junction and fills this hole, right? But remember, this guy has its parent, which is now a P plus, and this guy has its B minus, right? And these guys are fixed. Now this electron can fill that hole, right? And now what we have is this is gone, and now we have a boron and a phosphorus that are separated, right? So when you take a boron and a phosphorus and you separate them enough, then you create a voltage. You create a voltage. We've got 2 more minutes. We're almost there. You create a voltage, right? And you also create an insulating region, right? This is 2 things happen. 1, voltage appears, and 2, depletion occurs, which means that PN junction is insulating, right? But now you have a diode, and you also have a photovoltaic. you have a solar cell, right? So now, if this hole is filled with this electron, you've got an electric field between B minus and P plus, and now a photon comes in, is absorbed here, and that photon then excites an electron into the conduction band and leaves behind a hole in the valence band. Then what will happen is that this electron will go this way and this hole will go this way, because there's already an electric field there. And it's insulating except for those charges. And those charges experience the field and they flee into their respective N-type and P-type layers. And there you have, that is the photovoltaic effect. Okay? You heard it here first. Right? You're a one and only supplier of cool science nuggets. Oh God. I'm embarrassing myself here.
No,
Are you guys okay?
Yeah, this is great. This is great.
Excellent. Excellent. Good. That made my day and made my week. So I'm going to let you go now, and we will continue our conversation tomorrow if that's all right. Because your brains are full today, I think. Probably overly full. Where's all righty, cool. Good. All righty, guys. I will see you tomorrow. Bye.
Bye, thank you.
Bye, thank you very much.
You are very, very welcome. Thank you. Bye-bye.